Hi, and welcome back to Codex. Our speaker today is Assaf Goldberger from the Tel Aviv University. Professor Goldberger is an expert on configurations of points and lines. Today, he'll tell us about switching automorphisms and centralizer algebras. Take it away, Assaf.
Okay. Thank you very much, Emily. Thank you, John, Dustin, Michael, and any other organizer I'm not aware of. So it's wonderful for me to be invited to speak at Codex. It's a great opportunity. I think I met some of you guys in the summer in June, in ISOM, at ISOM. So I will be speaking about, let me share screen. Just, okay. Okay, it's full screen. Yes. So I was thinking about switching automorphism in central algebras with commutative and non-commutative coefficients. And this will be from a cohomological point of view. So here's the outline or overview of the talk. So for us, configurations are going to be ordered multisets. The order matters. A point can repeat several times in real space, complex space, and also it could be in a non-commutative setting like the quaternions. And they have a automorphism group, which is the main object of study. This is the group of self-switching equivalences. We'll define them below. If you look at the gram matrix of the vectors in the configuration, then this gram matrix is in fact a centralizing element of a certain projective monomial representation of the automorphism group. That's another way of saying that this group is a group of automorphism of this object. And this talk, we will establish a new interpretation of the automorphisms in terms of cohomology of groups and spaces. And we will generalize this view to non-commutative coefficients, specifically for nilpotent coefficients coming from a nilpotent group. Okay. So formally, we're going to encode configurations by matrices and by D matrices over some ring R. And R is going to be a general ring, which is going to be the coefficient ring. And we define the following notion of switching operators. They consist of combinations of the either of the four following types of transformations. First of all, we can permute the columns of the matrix. This is just permuting the points. We can have a unitary rotation, whatever that means in the context of a ring R, a unitary rotation of the rows. We can apply phasing, which means that we are allowed to multiply each column separately by scalar. And sometimes we define some restricted set of scalars. We don't want all scalars. We may want a restricted set of scalars. And there is a fourth option, which is traditionally not considered, which is Galois actions on the coefficients. So it might be the case that our configuration is algebraic, and the numbers of the configuration are defined over some algebraic number field, and then we can apply a Galois conjugation to the matrix. And we would like the symmetries to include also this type of transformation. And the definition is simple. The group of automorphism, the automorphism of the configuration phi is the set of all equivalences, all these equivalences that preserve phi as it is. Okay, let's move on. Here's just a simple example, just to put us on one page. We have this configuration of 4 vectors, A, B, C, D, ordered by this order. And here is a list of a few automorphisms. For example, we can reflect. We can have a unitary rotation with a unitary reflection, reflecting about the axis between B and C. So this gives you one symmetry. And then when you do this, you actually have to reorder. After you reflect, you have to reorder to get back the original ordering of A, B, C, D. Another option is rotation. We just rotate clockwise, and then we'll have to negate A and then reorder. And we can also apply a Galois group. This is an algebraic configuration, and the Galois group takes square root of 2 to negative square root of 2, and then A, B, C, D goes to A minus B, C minus D. And then if we negate B and D, we get back to our original. So these are automorphisms of this configuration. Also, as I mentioned before, the notion of projective representations is relevant here. So let G be a group. We define the notion of a complex projective representation. It is a map from G to the general linear transformations of V being a vector space, such that it's almost a representation, meaning that this pi respects products up to scalars. So this is not quite a representation. It's a slight generalization. And G prime satisfies what we know as the two cocycle relation. And this is actually what comes out of the associativity axiom of the action. So we have this cocycle. By the way, in this talk, I'm assuming people know the basic definitions of group cohomology. If this is not the case, if someone wants me to repeat it, I can define it. But otherwise I'm going to assume that this is known, and also some basic facts about group cohomology, like long exact sequences, are known. So this is my assumption. So this two cocycle defines a cohomology class in H2. This cohomology class has a name. It's called the Schur multiplier. And this is actually an invariant of this representation, meaning that if we can modify representation in 2 ways. We can of course conjugate it by some unitary. That's one thing, and we can also multiply each matrix pi of G by scalar, just modifying by scalar. So this is again a projective representation. If we do so, then the cocycle itself is going to change. It's not going to be the same, but the cohomology class will remain the same. So that's the cohomology class is actually an invariant of equivalence classes of projective representations.
Assaf?
Yes.
I know this audience, and I think you'd be safer sharing definitions about cohomology. Just as
Okay.
I think they don't.
Actually, I prepared. I have another presentation that I have in it the definition. Let me. So I think I'll have to stop share this one and go to another file. Stop share and then share again. And I think, let me see. I think it's here. I'm not sure. It's open in another program. I'm not sure how we can make it larger. Can you see this slide?
Yes.
Is it big enough?
Yeah.
There is also this, I believe it's a button that's in the upper right corner. There's a diagonal. I think that should.
Diagonal double arrow, right? This is two-sided. Oh, okay.
Perfect.
Okay, so actually here we have a definition of cohomology. So let me see. No, this is not relevant. So G is a group, and this group has also what we call a module. A module is in a abelian group mu, and the group G has an action on mu. And the action on mu means that the group G acts by automorphisms on mu. So it respects the action of G respects the abelian group structure of mu. Okay, so this is the basic setting. By the way, you can just assume. I mean, if it's more convenient, you can just assume that the G acts trivially on mu. Okay, although we will talk also about non-trivial actions. Anyway, we look at functions from n tuples of G to mu. These are going to be the cocycles. In a moment, I'm going to define cocycle. They're going to be functions from n tuples of elements of G to mu. And we're going to define boundary maps. So if I have a function from G to the n to mu, I can define a new function from one coordinate more from G to the n plus 1 to mu, DIF, by just saying, okay, DIF evaluated at G naught up to Gn is going to be G naught, and I'm going to multiply the I minus 1 and I elements in G together to get just an n tuple and plug it into F. That's for I greater than 0, and for I equals 0, there is we just drop the actually, there is another one. I forgot to put it. There is also dropping the last one. Okay, so I have all these DIFs, and then okay, this is kind of weird. I'm writing it multiplicatively. This is I'm just multiplying in the group mu all the results of DIF from I equals 0 to n. And this is DF. This is the boundary map. And we call F a cocycle if DF is 1. Okay, and F is a coboundary if F is D of something. And then the cohomology group is the quotient. We take the n cocycles. Coboundaries are cocycles, but they are in a sense they are trivial examples of cocycles, and they are interesting cocycles that are not coboundaries. And the quotient, telling you that I want to only see the interesting stuff, is going to be cocycles modulo coboundaries. That's the definition. It's a technical definition. To give you some insight about this definition, this is it's some way to linearize the group G. And the group theory is not linear algebra, and cohomology gives you a way to define some related vector spaces or abelian groups related to this group. So they are invariants of the group, and they allow us to study the group. So let me go back to the original presentation. I hope this was, I'm not sure how clear it was. I have to stop share and then reshare. So I think this is the one. So this is actually, when you see this equation, this is a 2 cocycle. So you see what you see is just multiplying elements of the group together, and you get this condition. So actually, one of the questions I want to answer is why cohomology? I mean, why do we see a cohomology? So in the original definitions, we talk about automorphisms of configurations, it doesn't seem to be related to something like cohomology, but actually we see it. We get projective representations and we get cohomology out of there. And actually, I want to explain this point. I think it's not full screen. Okay, let me move on. So there is, actually, I'm going to skip these two parts. Here is an example, which is, I think it's familiar to the audience. So let's omega denote the nth roots of unity. And we define the Heisenberg group. It's defined here abstractly. It defines by generators and relations. So there are three generators, mu, tau, and c. And actually, what all generators, mu, tau, and c, have order n. And c is in the center. C commutes with everything. And the commutator of mu and tau is c. So that's the Heisenberg group. It's the order of the group is n to the third power. And this actually has something which is known by the Weil representation, which is the representation that sends mu to the matrix M, the modulation matrix, which is the diagonal matrix with all roots of unity inside in the diagonal. Tau is sent to T, which is a circulant matrix. It's defined by Tij equals 1 if and only if j minus I equals 1 mod n, and else it's going to be 0. And C is sent to the scalar omega. So this is a projective this is a representation actually, but it's a true representation. It's not projective, but if we look at, if we mod out by the kernel, by the center, if we mod out by C, so we only care about mu and tau, we get a group which is abelian, which is just 2 copies of Z mod n, and this group has a projective representation. This defines a projective representation because the images of the mu and tau do not commute anymore, and they commute up to a scalar. Okay. Another important definition, a projective representation is monomial in a suitable basis if all matrices pi of G are monomial. So by a monomial matrix, I mean a matrix which is in every row and every column, it has exactly one non-zero entry. So it's like a permutation matrix, but you populate it with not just by zeros and ones, but you populate the ones by some larger class of scalars. So the Weil representation is monomial simply because these matrices, M and T, are monomial matrices. Okay. A general fact, let phi be a D by N configuration, and G is going to be the automorphism group of phi, not considering Galois. So I'm not, at this point, I'm not considering the Galois actions, just the traditional ones. Then G possesses a projective monomial representation defined by the reordering and scaling matrix. So this means if you have an automorphism, the automorphism consists of three things, right? It has unitary rotation, and it has also reordering and scaling. So if you just think about the reordering and scaling, you get a monomial matrix, which does that. And this gives you a monomial representation coming from the configuration. And we denote it by pi phi. And the fundamental fact is that the Gramian matrix, the Gram matrix of this phi commutes with pi phi. So this is what we call a centralizing element of the projective representation. And another fact is that monomial representations are induced from a one-dimensional character on a subgroup. So it's always, if you see a monomial representation, it's always going to be an induced representation from a one-dimensional character of some subgroup, and vice versa. So here is an outline how we can construct configuration given the automorphisms group, and more precisely, given. So I'm not insisting on the precise automorphism group. I'm insisting of giving something in some subgroup of this automorphism. So I want to design a configuration that has a given automorphism subgroup. And the way we do it, we fix this group, and we pick a cohomology class in the second cohomology class with complex coefficients. And we compute a covering. This cohomology class defines some surjective map between between some covering group G tilde and G, and then induce from a one-dimensional character to obtain a monomial representation of G tilde. When we reduce this to G, we get a projective representation. And then once we got a projective representation, we compute the centralizer algebra, the collection of all matrices that commute with this representation. And finally, we pick a self-adjoint positive semi-definite element in this algebra. And this will be, and anything like this will be a gram matrix of a configuration with this automorphism subgroup G. So this is, I think this is well known to this audience. And the objective of my talk is to give you another point of view on this. By the way, if we are interested in Galois, then we can actually the cost of considering Galois is that we have to use what we call semilinear representations. So semilinear representation means that scalars don't quite commute with the operators, but if we let a scalar pass through an operator, this will cost us in some Galois conjugation of the scalar. Okay, like I think at least for complex conjugation, this should be familiar. So if we are doing everything like this with respect to semilinear representations, then we can construct configuration that also have this Galois feature. Okay, so here the next section is actually the central section of our talk. We call it cohomology development. So it's essentially a way to construct configurations with given automorphism subgroups, but not using representation theory, using instead tools from cohomology. And actually, this will lead us to on the one hand, to some insights that will explain the role of cohomology in this construction. And on the other hand, it will give us ways to generalize this further beyond representation theory. So the basic setting is that we start from a G, a finite group, and X is going to be a finite G set. So this is a group, this is a set that G acts on it. And we fix a group mu, and actually I did not write here, I should have written that I'm going to assume that the action on X is transitive. So there is just one orbit of the action on X. So you want to think of X as the index set of the matrices that we will construct. Okay? And we fix a group mu, which is going to be the group of coefficients. So we're going to consider coefficients in mu. And this mu is going to be also a G module. This means that we are allowing G to also operate on mu. If you want an insight about G modules, I would say that if you consider, a lot of times you want to consider complex conjugations. So you might want to have some symmetries of your configuration that allow complex conjugation on coefficients. So this means that you want your symmetries to act by complex conjugations, some of them at least. maybe half of your symmetries want to act by complex conjugations. And this is you want to say that the group of complex non-zero complex numbers is a module over this group. Well, this group acts on it by either by trivial or by complex conjugation. But we can allow even more. Here is an example. You take mu to be the complex number without zero. That's exactly what I said. Elements of V may act trivially or by complex conjugation. Okay, write mu plus. So we are going to allow, so mu typically is going to be elements which are non-zero. And we're going to artificially add a 0 point to mu. Okay, so it's not a group anymore, it's actually a semi-group. Zero is an absorbing element. And 0 is fixed by G. And we define an X matrix is going to be a function from X cross X to mu plus. So this is this is like saying that our matrix is indexed by X. So it's like for every pair of points in X, we get an entry, which is defined by this A. And the support of A is going to be a subset O where A is not zero. Not zero means it's in mu. Okay, we'll restrict attention to supports that are stable for G. So, so obviously since G acts on X, it acts also on X cross X. And the supports we want to consider are also need to be stable under the action of G. So fix as G stable and consider a set MO of all X matrices with support O. So these are all functions, A from X cross X to mu, that are supported on O. Here's just an example, a visual example to see. There is a definition. A G stable O is partitioned into G orbits called orbitals. So here is an example. We take O to be the support to be all X cross X, and this is this matrix is colored by 3 colors, each for an orbital. So if this is actually a true example derived from taking G to be the A5, the alternating group of 5 elements, a group of order 60, and X is a specific set of order 10. And if you look for the orbital decomposition, you will get this picture. Okay. Now, so remember, MO is going to be the set of all matrices supported on O. So we're going to define an action of the group G on matrices. How the action is going to be simply by acting on the indexes of the matrix, the index set, okay, and on the coefficients. So this is why you get a G out, which is the action on coefficient, and inside, this is the action on the index set of the matrix. Okay, next. We say that 2 matrices are delta equivalent if they are just diagonally conjugate with with values in mu. And we denote it by A equivalent delta to B. And here is the definition, the fundamental definition that I'm working with. A matrix A in MO is cohomology developed with respect to the data G, X, mu, and O. If whenever I act on this matrix by G, I'm going to get a result which is equivalent, diagonally equivalent to the original matrix. So what actually this means? This means that if I act by G, so what I'm doing is I'm reordering the index set of the matrix. This is like ordering if you think of this matrix as the Gramian of something, it's just like ordering ordering the rows and columns of this Gramian by permutations. And then to get back to original matrix, you have to rescale. You have to add correct phases in rows and columns. This is the delta equivalence. So this is actually another way to say that this matrix A has G as automorphism subgroup. And as we'll see in a moment, this is the definition which will be the way that will be most fruitful to us. Just a few comments. We wish A to be invariant under some monomial action. So actually the monomial action is the combination of the permutation and the scaling. We separate the combinatorial. This equation is actually has the left-hand side and right-hand side, and the left-hand side talks about the permutation, and the right-hand side talked about the scaling. So actually, this way we just put these two types of actions on both sides of the equation. And also, crucially for this setting is that the right-hand side, if it's not written well here, if you see the group of all diagonal changes is actually in abelian group, because diagonal matrix multiply just element-wise. Okay, and this is a big advantage for us. Now, before I go into cohomology, I want to say, a disclaimer. What I'm saying now is actually that everything is linear algebra. So what do I mean by this? I mean, if I want to compute a matrix which is a cohomology developed, okay, it is possible to put it in a form of linear equations. Why? So in a sense, all of these operations that you see in this equation are given by multiplications in mu, in the group mu. I mean, the diagonal is just multiplying the diagonals with the entries of A, and this is just a permutation. It's just a combinatorial object. If you ignore conjugation for a moment, it's a combinatorial permutation, and here you get something which is multiplication from both sides by some D. But if you think of the mu additively as an additive group, it's just additions in the group. So essentially, it's a linear. You can consider this as a linear equation in A, or a system of. If you go over all groups of A, you get a system of linear equations in the variable A. You say I want with some other delta, which is also, you can take it as a variable, but essentially you're just interested in A. So these are linear equations, and actually doing linear algebra over abelian group is not that difficult. You can use the primitive that you can use for doing linear algebra is the Smith normal form. So essentially, you can solve, if we want to understand what are the matrices A that satisfy this condition, then you solve a linear system of equations over mu. And this is just to give an example to make it simple. Suppose your mu is just plus or minus 1, okay? Then when you linearize it, you think of plus minus 1 as an additive group of 0 and 1. And all these operations become just operational linear algebra over GF2. So it's actually very simple to solve it. And the only objection I have for this is this is not very informative. So you get a system of equations, you can solve it, you get solutions, but what can you say about them? It doesn't give us much insight. So we're going to do the following. We're actually going to divide by delta. So here is a list of few groups or G modules that we want to consider. The MO are the matrices which we supported in O. Essentially, these are functions from O to mu. Delta is going to be all functions from O to mu that have this specific form. There are some D of A over D of B. D is going to be the matrix, all functions from X to mu. And these are going to be, this should be viewed as diagonal matrices. And we have the group mu. And now what we want to do, we want to look at the quotient of MO mod delta. This is exactly dividing by the relation of being delta equivalent. But this is just rewriting this in the language of groups. So the group MO divided by the group delta is exactly the group of matrices modulo delta equivalence. And when we do this, the condition that we wrote before becomes more simple. We just say that these matrices are invariant under G because we divided by delta equivalences. Okay, so this means if you know a little bit about cohomology, this means that this means you want to compute the zero cohomology of this quotient module, MO modulo delta. This is just the zero cohomology is the same thing as the G invariance. Okay. Now, so actually, before I go to the next slide, I want to explain the point of view. So you want to compute this H0. H0, it looks simple, but it's actually it's a complicated object. It's not a trivial to understand what are the invariants in this quotient group. Okay, and the way we solve such a problem, we say, okay, we have a complicated module, and we want to simplify it. And the tool we're going to use to simplify modules is what we call resolutions. So we're going to make a resolution of this module into simpler modules, and this will give us a way to compute this invariant module in terms of the resolution. So this is the way it goes. So the resolution is here. This is this line tells you that you have a complex. You have a complex which is here is your module MO modulo delta, and there is a map from MO surjective to MO modulo delta, and the kernel comes from a map from D to MO, which is defined by taking a function of a single variable and producing, which we call D, and producing a two variable function by D of A over D of B. That's the map from here, and it has a kernel, which are the scalars, the mu. Now this comes with a caveat that in order for this to be a resolution or to be exact, is that the set O has to be what we call irreducible. What do we mean by irreducible? It means that you think of O as the support of the matrix. You can think of it as a graph. It's like an adjacency matrix of a graph, or actually a directed graph. And we say that it is irreducible if the underlying graph is connected. It's connected as an undirected graph. Okay, this is and it turns out that that's the proposition here says that this sequence actually is exact except maybe for mu, but it's exact at mu precisely where this O is connected. So what you see, I want to amplify that there are some topological quantities or topological concepts that, like connectivity, that enter this analysis. And if this O is connected, then we have an exact sequence, and things are simpler in a certain way. So here's the resolution. And actually, this resolution, we break it down into two parts, two short exact sequences. The first one is saying, okay, MO goes to MO modulo delta with kernel delta. Delta is just the image of D inside MO. And another sequence, which is this. And now, one of the features of cohomology is that when you have a short exact sequence of modules, you get a long exact sequence of cohomology groups. And so here is the red is our intended group. And you get this fits into a long exact sequence. And on the two sides, you see H0 GMO, and MO is a simpler module, and I'll explain it in a moment why it is simpler. And then we get another group on the other side, which is H1 of G with module delta. And if I want to compute it, I'm going to the second short exact sequence. And H1 G of delta sits between two groups either. One is the cohomology of D, and the other is the second cohomology of G mu. Now, this second cohomology is actually the same second cohomology we've seen in the projective representation. Okay. Now, to simplify this even more, we have a well-known theorem which is called the lemma of Ekman-Shapiro, which deals with induced modules or induced representations. It tells you that the cohomology, if you have a set S that is broken, it's a union of G orbits. So there is a decomposition of a G set S into orbits. And if for each orbit we take a point and we take the stabilizer of this point, then there is an isomorphism of the cohomology of G with this is going to be the permutation module. This is actually the induced module. It's a module based on the set S with coefficients in mu and set S, and the group acts on the coefficient and also on the set. And it tells you that this cohomology can be computed in terms of the orbits and the stabilizers. So it reduces the cohomology from the B group into the stabilizers, and we get one contribution for each orbit. And also the module is simpler. It's just mu instead of mu of something. This is the lemma of Ekman-Shapiro. And what it means actually that if we compute the cohomology of G with respect to the module D, we just get the cohomology of the stabilizer of a point in X with mu. And also the same thing, if we take the cohomology with respect to O, actually it should be MO, not O. It's a typo. This is going to be the cohomology of the stabilizers of points in the orbits, in the orbitals. So actually, this is just rewriting this two long exact sequences in terms of the Ekman-Shapiro. So you get that actually this group has contribution from this group, which is just numbers. These are just numbers. I'm just picking out for each orbit. I'm just picking out an entry in mu, which is invariant under the stabilizer. And on the other side, we get this cohomology, which also has two sides. One of them is the first cohomology of Hx, and the other one is H2 G mu. And I'm going to explain this more in a moment. Roughly speaking, CDMs, cohomology developed matrices, are determined by the following ingredients. There should be values in mu to the hi. So for each orbital, there is one value. A suitable cohomology class in H1 G delta, which is composed by these two. So there's going to be a cohomology class in H1 Hx and then a cohomology class. So essentially, we have three layers here. We have a layer that comes from the orbitals. We have another layer that comes from the index set X. And we have another layer coming from the coefficients of the matrix mu. And from these two, from these three layers, we are able to compose the matrix. And in a moment, I will give you an example. Okay, let me just tell you about the interpretation. For the first layer, A0, put a value in each orbital and spread it along the orbital. So this is just if you think of matrices which are invariant under the group, then you just, for each orbital, they are determined by just one value of the orbital. For example, think about circulant matrices. Circulant matrices are invariant under the action of the cyclic group, right? And the orbitals are the cycles in the matrix. And in each orbital, you just need to know one coordinate in each orbital to spread the whole matrix. Now, the class in H1 here is actually an analog of the character from which we induce to G. Remember that in the representation theory, we talked about induced representations that give us monomial representations. And actually, the class in H1 is actually the analog of this character. And the class in H2 is actually the Schur multiplier of the projective representation. So this is the dictionary between the two interpretations. So here is a special case. I want to talk about this special case, which maybe will explain more about this. So assume that the set X is the same group, is the group G. Okay, and actually, what this tells us that all the cohomologies with the stabilizer are going to be zero. It's going to be simplify a lot. And what we get from here is actually that this sequence, that this H0 is composed from two layers only. So all the H1s are going to disappear. And we have the two layers. One of them is values in orbitals, and the other one is the Schur multiplier. So only these two are going to be the pieces that construct our matrix. And here is a theorem. We call, by the way, we call these matrices cocyclic matrices, and it will be clear, the definition will be clear in a moment. So here's the way we construct a matrix. You see here, X and Y are going to be elements from X, which in this case is the group G. And you see actually two variables, or two variables, which are F and omega. What are these? F is going to be just a function from G to mu. So it's going to, there is going to be just, for every element of G, I'm going to tell you a value in mu. This is what F does. And the other one is some formula with omega, and omega is a 2 cocycle. And if you give me these two pieces, F and omega, then I construct this matrix. And this matrix is exactly the cohomology developed matrix constructed from these two pieces of data. So we'll see concrete examples in a moment. So these are called cocyclic matrices because actually they are designed by a cocycle omega. The comments are that cocyclic matrices were originally discovered in relation, they came from combinatorics. I think something like 20 years ago. People were studying an object, combinatorial object called pairwise combinatorial design. And they discovered a way to construct them by using a cocycle. They were not aware of the cohomology theory behind the cocycle. They just saw that their function satisfied the relation, which eventually they discovered it was the cocycle relation. But this is strictly came from combinatorics. And much later, it was discovered, the connection to automorphisms. It is believed that any order 4M, for every order 4M, there is a cocyclic Hadamard matrix. That's one conjecture that is believed. Let me give you some examples. So here we have the translation matrix. It's the modulation matrix. Tau is going to be the primitive root of unity, the modulation and translation matrix. And we define what I think people here know, the Gabor frame. We take all the m to the I times 2 to the j, apply to a single vector, and get n squared vectors and this constructing configuration. And we compute the Gramian matrix. And this turns out to be a cocyclic matrix with respect to the group Z mod n cross Z mod n. And if you ask what is the cocycle, it's going to be given by this formula. The cocycle takes two group elements. AB is a pair, which is an element of the group. CD is another element of the group. And we compute tau to the b times c. This happens to be a 2 cocycle. So this is a cocycle matrix. Another well-known example is I call it the Det Fourier matrix, but I don't think it's the conventional name. This is the matrix that you take indexed by pairs of elements modulo n, and the position at A, B, C, D is going to be the tau to the determinant. So this is an orthogonal matrix. It's a Hadamard matrix, and it's also cocyclic over the same group, and the cocycle now is the determinant. Actually, this is exactly the cocycle. The omega here is the cocycle. Also, another example, which may be less well known, is the Paley Hadamard matrix or Paley ETF grams. They happen to be cocyclic over the dihedral group. Okay. How much time do I have left?
Well, we started a few minutes late since I hadn't written the intro, but should be kind of tying things up right now.
Okay. Yeah. So actually, I have here a topological interpretation of what is going on here. I'm not going to talk about it. It's more involved. So I think what I want to do is talk a little bit about non-commutative coefficients. And the problem with non-commutative coefficients, so mu is going to be a non-commutative group now. And we can still define the same notion of cohomology development. Okay, we can say look for all matrices with values in mu that are, when operating on them by G, we get something which is delta equivalent over this mu. So this makes perfect sense, this definition. The problem is that it seems like it's going to be difficult to describe this in terms of cohomology, because cohomology theory is not really well developed over non-commutative coefficients. There are there is a way to define the 0, 1, and second cohomology, but they are not groups; they are just sets. So it's really not. And higher cohomology is even. I'm not sure it's even defined. And in a sense, cohomology, the reason that we used cohomology is because everything was linear algebra. We thought of mu as something additive. And we could write this equation, we can interpret this equation like a linear equation. So doing cohomology is essentially doing linear algebra. It's not more than linear algebra in a sense. And when we have non-commutative groups, then this is, of course, things are not linear anymore. So what do we do about this? So the answer, the honest answer is that I don't know. But I do know some partial answers to this. And one of them is when we consider nilpotent groups. So if we allow mu to be a nilpotent non-abelian group, then we can actually go quite a few miles towards this goal. So this is just telling you that we can do linear algebra over nilpotent groups. This is like doing linear algebra over nilpotent groups is just doing them step by step. You have abelian quotients. You solve modulo the quotient, and then you have some residual equations, and you solve them again modulo some other quotient, etc., etc. So this slide explains how to do linear algebra in the nilpotent setting. And this actually carries also to solvable groups as well. So just to wrap up things, we actually want to look at like before at the resolution, but these things are non-abelian groups. And if we divide by delta equivalence, then this is even worse. So I get some sequences of things which are not even groups, they are sets. But there is a notion of this being exact, and this notion is actually explained here. I'm not going to go into too much details. So I think I'm going to say only the following. Let me see. So we have this theorem tells us actually how we compute the H0 of a nilpotent with nilpotent coefficients. In a special case, actually in a more special case, that this nilpotent group has 2 stages only. It's what you call a meta-abelian group. And if we do this, we actually get a sequence. So this red thing is just a set, it's not a group. But the blue things are group because they actually talk about the graded pieces of the nilpotent groups, which are abelian groups. And we get something like a long exact sequence between cohomology groups, and we are able to compute this element by computing these two cohomology groups. So I begin with something in the quotient, which is abelian, mu bar is the quotient, and I'm computing this H0 like before, like we did before. But this does not always lift up to mu. There is an obstruction which lies in the first cohomology of some complicated module. And actually, here I give a little bit information how to deal with this complicated module. I'm only going to say that I was able to compute one non-trivial example of this process and obtain the cohomology developed matrix over a nilpotent group. So I think maybe I should stop here.
All right, well,
Yep.
thank you very much. Let's smash that reaction button
Okay.
and stop the